This is Mr. Precella working a little intro to probability theory with his Math 1324 class. A very large class today, I must say. No, it's a very small class today. It's extremely cold outside for South Texas, okay? To begin this probability theory, the first thing I'm going to do is define this is just a little intro to probability theory. The first thing I'm going to do is just define what's called a sample space. A sample space is a set of all the possible outcomes of an experiment. And when we say experiment, when we're talking about probability, we don't mean a lab experiment, like a chemistry experiment. The sample space is the set of all possible outcomes of an experiment. By experiment, we mean something like maybe they're tossing a coin. You're trying to figure out if a coin is a fair coin, or has it been rigged, making one side heavier so that the other side comes up. Or maybe if you're looking at dice, are they fair dice, or was one side made heavier so that the opposite side would come up more often. If we were talking about tossing a coin, the sample space would be, if you're going to toss a coin, how many outcomes are possible? Only two. Okay, and what are they?
Heads and tails.
Heads and tails. One of an outcome that couldn't happen if you're tossing a coin is September. Okay, that wouldn't be a possible outcome. You're going to get a heads or tails. Okay. On our first problem, it says, okay, write a sample space for the following random experiment. And what's the random experiment? Well, a month of the year is chosen for a vacation. So we're just randomly choosing a month of the year for a vacation. How many possible outcomes are there going to be if you're going to randomly choose a month? 12, okay? So there's not a lot of work to it. You just sort of read the problem and choose A, B, C, D. Which one would you, just glancing at it, definitely you wouldn't choose? Yeah, hey, that 1 through 30, nah. So which one of these goes January through December, listing all the months? It's sure not C, is it? Y'all see, is it sort of hard?
D.
D. It's not B because B includes Monday, and Monday's not a month of the year. This is called a sample space. That's what statisticians refer to as a sample space. Now, we're going to be looking at just what's called empirical probability, which is just sort of looking, counting things. You're just going to sort of count it out. The probability that some event E occurs is going to be the number of ways E could occur over the number of possible outcomes. The number of possible outcomes is however many outcomes are in your sample space. The number of ways the event could occur over the number of possible outcomes. So, number 2, the word die, that's singular for dice. Okay? Number 2 says, use the basic probability principle, that's what I've written right here, to solve this following problem. Express each probability as a fraction. Okay, so a 12-sided die is rolled. Have y'all ever seen one of those? Die is singular for dice. Most die have just 6 sides. But there are 12-sided die. I don't have one of those in here with me. And if you had a 12-sided die, then the possible outcomes, the sample space would be, well, what could you get? A 1 through 12. So we want to know, what's the probability of rolling a 7? Well, how many 7s are there up here? 1. How many possible outcomes are there? 12. Probability of rolling a 7 is 1 over 12. Okay. If you've made it this far, this is not going to break you. Okay. If you can make it past that simplex method, then I'm not the teacher that's going to break your spirit, and this is not the course. Okay. You're wondering what the heck am I talking about breaking spirit? It's a long story. With a student at a bar, a student telling me a few years back about his math teacher breaking his spirit. Okay. And I was unsympathetic. I was late at night. And I wasn't my usual self where normally, when someone comes up to me and says, "You teach math?" Yeah. Oh, my turn, but let me tell you how much I hate my teacher. And he starts talking, and I'll make the noises. But I was too tired to make the noises. I sat there at the table thinking, "Go away." My brother was there, and he'd gone to the bar. I shouldn't be telling this story on a video. Remember, my name's Timothy Precella. Anyway, and he just talked about how much his math teacher broke his spirit. My brother eventually came back and said, "Oh, wow, that was such a sad story. What was wrong with you? You seemed mad. You weren't even," we talk about making the noises. You make the polite noises. "Oh, okay," And I was like, "I'm too tired to make polite noises." So if I haven't broken your spirit yet, this isn't going to, but I'll keep trying. Problem number 3. Here it just says a single fair die is rolled. Find the probability of rolling a number greater than 1. Well, it's not. Don't assume a 12-sided die. We're assuming just a normal die. That's singular for dice. When I first heard that years ago as a student, I thought, that's a stupid word. Did y'all know that? Dice is plural for die. Dice is the plural form of die. I didn't know that. I thought you could have one dice, but that was way back when I was a teenager. Okay, so what's the probability of rolling a number greater than 1? Well, here's all the outcomes. So there are 5 ways you could get a number bigger than a 1 out of what? 6? Okay. Oh, wow. Number 4. I'm just sort of flying through these. Let's see, that's that old 12-sided die coming up again. And this time, however, it says, find the probability of rolling a 3 or a 12. Notice they wrote out all the outcomes. And number 3, they didn't. I had to do that. Okay. So a 3 or a 12. What would y'all think that's going to be? It's going to be 2 over 12, which I'll reduce to 1 over 6. Sort of flying through some basic probability theory. I'm trying to get as much of these done. It's not really long or hard. It's a nice, gentle way to end the semester. Number 5. A little table. Number 5. It says, use the table to find the probabilities that a person's total charges during the period are the following. Okay, so let's look at this table here. The table shows the probability of a person accumulating specific amounts of credit card charges over a 12-month period. So the probability that the person charges under 100 would be 0.31, which is a percent would be 31%. And the probability the person charges over $10,000, just 1%. And so I'm not going to read the whole table to y'all, okay? Let's see, what does first one say? What's the probability that a person's charges are between $2,000 and $29.99? So basically, this is, can you read the table? Is it 0.07? Which would be 7%, but we're writing it as a decimal. What's the probability that a person's total charges are less than $5,000? Ooh, what are we going to have to do with that? It's less than $5,000. It's going to take a little bit of work. Less than $5,000 would be all of these. So what am I thinking we're going to have to do? Add all of those up? Just add them up? Is it going to be 0.92? Let me see. 0.31 plus 0.19, that would be 0.5, plus 0.15 plus 0.13 plus 0.07 plus 0.07, yeah, 0.92. In order for this table to make any sense, all of these probabilities should add together to give you a 1 or 100%. And so when I said, is that a 0.92 a while ago? What I was doing was adding the 0.07 and the 0.01 to get a 0.08, and then I subtracted. It might be easier thinking of these as percents. All of these should add up to give 100%. So 100% minus 8% would leave us 92%. Now, what about the last question here? What's the probability that a person's charges are over $49.99? Would I add 0.07 and 0.01? Okay. Now, something called odds. Sometimes people get odds and probability confused, but there's a difference between odds and probability. Generally, if you're in Vegas looking at horse races or boxing things, they're going to give you the odds. They don't say the probability. They say the odds of the person, the horse or whatever winning. The odds in favor of some event E. Maybe the E is blah blah is going to win the boxing match. Or maybe Lucky Lou is going to win the horse race or something. The odds in favor of event E, formally defined, it's the number of ways E can occur to the number of ways E cannot occur. Okay, well, the next two problems are going to involve a pair of dice. And I'm going to need to write out all the possible outcomes. It's easy if you're just rolling one die. The outcomes are 1 through 6. But can you imagine, let's suppose you had a red die and a blue die and you were rolling them. There'd be a lot of outcomes. Okay, so I'm going to write them out sort of as ordered pairs. And it's going to look strange at first, but we're going to need this little diagram to do problems 6 and 7 for the homework. For test purposes, I don't think I'll be so mean as to make you have to write all of this out. But I'm writing these as ordered pairs. I'm rolling 2 dice. So think of it as first die, second die. You could get a 1-1, or you could get a 1-2, a 1-3, a 1-4, a 1-5, or a 1-6. Could we get a 1-7? No. Okay? So that's all the ways you could get a 1 on the first die. Maybe think of them as red and blue. Well, think roll it once, pick it up, roll it again. Or you could have gotten a 2 on the first one. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, and so forth. If I'd been thinking, I would have written these out beforehand, but I didn't. So 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3. Wow, am I glad this didn't say 2 12-sided die rows, okay? 4, 5, 4, 6. Okay, 20 short years will be through. Well, no, y'all can't complain about having to write up this after everything y'all have done. That simplex method and all of that. Okay, finally, okay. A 6 on the first one, a 1, or a 6, 2, or a 6, 3, a 6, 4, a 6, 5, a 6, 6. Now by writing them out like this, if we were looking at the sum of the two die, if you look at the diagonals, right here, that's a sum of 2. I'm just going to go through, drawing a line through each little diagonal. Like here, these two have a sum of 3. Here are 3 that have a sum of 4. Why am I doing this? Well, the problem we're going to solve is asking what are the odds of rolling a sum of 10? Okay. Here, these have a sum of 5. Here's my invisible orange. This orange ink is hard to show. Those have a sum of 6. This big diagonal, sum of 7. In 20 short years, we'll be through a sum of 8. A sum of 9. There are 3 ways you could have a sum of 10. I think that's going to be important, isn't it? 2 ways you could have a 11. Would it be possible to ever have a sum of 12? Excuse me. It is possible to have a sum of 12. Would it be possible to have a sum of 13? Well, no, not on our little. So, problems 6 and 7 aren't long problems if you have these outcomes listed. So you might want to keep up. If you're writing them down now, you might want to keep up with them. If not, maybe if you click View an Example, it'll show them. Okay, if you don't want to have to write them all out. So, a pair of dice is rolled. What are the odds of rolling a sum of 10? That's different from what's the probability. Altogether, did y'all count how many outcomes are possible here?
36.
36? So if it said what's the probability, you would go 3 over 36. But it says what's the odds. So how many ways could you get a 10? 3 to what? How many ways could you not get a 10? How many ways are remaining?
33.
33. So 3 to 33. If you punch that into your My Math Lab, it'll probably say wrong. Why will it say wrong? Well, we reduce odds the same way you would reduce a fraction. If you had the fraction 3 over 33, what could you do to reduce that fraction? Divide both of those numbers by 3. Divide both of these numbers by 3. Instead of saying 3 to 33, it's going to be 1 to 11. Okay. The odds of rolling a sum of 10, or 1 to 11. You reduce odds the same way you would reduce a fraction. You wouldn't say the odds of some event were 2 to 4. You could reduce that to 1 to 2. Right? Just like you could reduce 2 over 4 to 1 over 2. Are y'all caught up? The next one, okay. More of these are. No. Oh, this isn't odds. Okay. It moves to probability now, but it's still a pair of dice, so we're going to be using this. Okay. Find the probability of rolling a sum not more than 3. A sum not more than 3. Do you see what I have this little thing here? Not more than 3 would be a sum of 3 or less. So it would be, how many ways could you get a sum of not more than 3? Well, 3 over what? What am I going to put, 33 or 36?
36.
36. This is probability. And that we could reduce to 1 over 12. Now what about finding a sum? Probability, but there'll be more problems with odds in a little bit. A sum not less than 4. Not less than 4. That would mean it needs to be 4 or bigger, right? A sum not less than 4. Can I coerce y'all into agreeing that would be 4 or larger? So how many ways could you get a sum of 4 or bigger? Well, there's 3 here. How many are there altogether? 36. So could y'all guess how many ways you could get a sum of 4 or more? It would be what over 36?
33.
33 over 36, which we could reduce by dividing by 3 to get
11 over 12.
11 over 12. I'm following this. Now finally, the third part.
You still count the 4?
A sum not less than 4 would be 4 or bigger. Okay? 4 or bigger. Not less than 4. See, 4 isn't less than 4, so you've got to include 4. Okay? What about a sum between 6 and 11, and then it says exclusive? Exclusive, what does that mean? Is it going to include the 6 and 11? No. Okay? So you're looking a sum between 6 and 11, that would be sums of 7, 8, 9, or 10. So how many ways could you get a sum of 7, 8, 9, or 10? There are 6, plus 5, 11, plus 4, 15, plus 3, 18? Am I adding those up right? So it'd be 18 over 36, which would be what? What would I type in for my math lab? It says type an integer or a simplified fraction. That would be 18 over 36. Would that reduce to 1/2? Okay. Just doing a little probability theory. This is the last homework assignment. See, when we need number 11, we're going to be using a pair of dice, so I'll get my little chart back. But right now, let's see, number 8. The math faculty at a college consists of 4 professors, 8 associate professors, 11 assistant professors, and 6 instructors. If one faculty member is randomly selected, find the probability of choosing a professor or an instructor. Well, they're randomly choosing one of these faculty members. Does it tell us how many faculty members there are altogether? No, we're going to have to add them up. So what's the total number of faculty members? 4 plus 8 is 12, plus 11 is 23, plus 6, or the 29 faculty total. We want to know the probability of choosing a professor or an instructor. So there are 10 ways of choosing a professor or instructor. There are 10 of those out of 29. So 10 over 29, and it says write a fraction. Eventually it's going to start saying, oh, use decimals, and we'll have to punch it in our calculator maybe. Okay. Back. I'm going through this quickly. Any questions? The next one, back to odds. A single fair, can y'all read that with my purple ink there? It's a single fair six-sided die is tossed. In probability, we always talk about fair dice. And the reason for that is because, you've heard of loaded dice. Make one side of a die heavier than the other side's going to come up more. Okay, so we say a fair die, meaning it's not loaded dice. Find the odds of rolling a 1, 3, 5, or 6. Odds are different from probability. So we want to know how many ways could you roll a 1, 3, 5, or 6? Well, just 4 of them. You're rolling one die. So how many ways could you get a 1, 3, 5, or 6? Well, 4. 2. How many ways could you not get that 1, 3, 5, or 6? 2. When you're working with odds, these two numbers should add together to give the total number of outcomes. Okay? But we're not going to write 4 to 2 because we got to simplify this the same way we would a fraction. How am I going to simplify it? 2 to 1. Okay. Oh, here's another odds problem. Number 10. A single fair die is tossed. Find the odds in favor of rolling a number greater than 2. A number greater than 2. Well, I guess I should have written out all the little outcomes. If you're just rolling one die, don't look at this. Okay? Look at just rolling just one die. The next one we'll need to look at this. Okay. Here are all the outcomes. We want to know the odds in favor of rolling a number bigger than 2. Does that include 2? No. So there's 4 ways you could roll a number bigger than 2. Oh, wow. To what? 4 to 2. Okay? I said, oh, wow, because I think it's going to wind up with the same answer that we got on this other one here. Okay? With odds, how many ways can you roll the number bigger than 2? How many ways can you not roll a number bigger than 2? So it would still reduce to 2 to 1. Hey, you know what? I wonder if I write this in, is it legible? In the little box, that's where y'all type your answer in. Just sort of flying through. It's just a nice introduction to probability theory. Let's see. A pair of dice is rolled. What are the odds of rolling a sum of 4 or a sum of 11? Okay, so what are the odds of rolling a sum of 4 or a sum of 11? So how many ways could we get, I'm looking back at this little chart here. How many ways could we roll a sum of 4? 3. What about 11? 2. So there are 5 ways that we could get that 4 or 11. So it's going to be 5 to what? 31. Yeah, 36 minus 5, 31. And I don't think that one's going to reduce, is it? It's just 5 to 31. Okay. Notice the two numbers should add together to give the total number of possible outcomes. With that in mind, what we're about to start doing is converting between odds and probability. How do we convert between odds and probability? Like right here on this one, these two numbers have to add together to give 36, the number of possible outcomes. So what, on this one here, find the probability that a bachelor degrees recipient in 2006 majored in elementary education is 39 over 100. Find the corresponding odds. Here we're given the probability. We want to write it as odds. Well, I'll get it started. It's going to be whatever this top number is, 39 to what? What will this bottom number be? How do I calculate it?
61.
Oh, yeah, okay. I didn't expect that to be so fast. Okay, 61. How did you get that number? You subtract 100 minus 39. These two numbers should add together to give the total number of possible outcomes. Okay. So y'all are getting this. Okay, so 39. Well, I don't think I can write it in that box. Oh, there it is. 39 to 61 there. So what we're doing now is converting between odds and probability. When you do the odd, when you have the odds, the top number is the first number, the bottom number is the sum of these two numbers. With that in mind, let's see if what it says on number 13 about Nolan. The odds in favor of Nolan getting promoted are 9 to 1. Find the probability that Nolan gets promoted. 9 over 10. So here's a 90% probability. Odds of 9 to 1 mean a 90% probability. Right? Odds of 1 to 1 would mean a what percent probability? 50% probability. A 1 over 2.
Oh, so
Okay?
1 to 1.
Odds of 1 to 1.
I was thinking.
Okay? Okay? Now, something that sort of shocked all of us in April, the THECB, Texas Higher Education Coordinating Board, Academic Course Guide Manual, this was April 2013. They up and started listing student learning outcomes for this course, and they were like, okay, introduction to probability, and then they went as far as to say, including expected value. None of us were doing expected value in the course. And they're like, oh, okay, it's not hard. Now we're going to, so here's something new, expected value. It's sort of a way of calculating an average. What we have here is what's called a random variable, and this whole table can be referred to as a probability distribution. X is some sort of event. The probability that X equals 2 is 0.2. The probability of X equals 3 is 0.3. The probability of X equals 4 is 0.1. The probability of X equals 5 is 0.4. This is called a probability distribution. It lists all the possible outcomes, and all of these probabilities, can you add them up in your head? What should they be? Or what are they?
1.
A 1, okay? So these are all the possible outcomes. If it asks what's the probability that X equals 6, 0, okay? Here are all the possible outcomes. To calculate the expected value, if all of these had an equal probability, then the expected value would just be the average. So what some people think of the expected value as a weighted average. And I'm going to write it out how you calculate it here, because I can't really pull up my virtual calculator and show it to you while I'm doing this. You're just going to multiply x times its corresponding p of x. 2 times 0.2. Why do I use parentheses? I'm going to use a little star. Plus 3 times 0.3 plus 4 times 0.1 plus 5 times 0.4. This is called expected value. To calculate the expected value, it's the sum of the x times corresponding p of x. So, what do I have in here? I have a lot of stuff in here. This is one of those times you won't be able to see the screen worth a darn, but on the video they always look nice. I'm just going to patch in what I've written there on 2 times 0.2 plus 3 times 0.3 plus 4 times 0.1 plus 5 times 0.4. No, if y'all need help patching and multiplying and dividing in your calculator, I'm really insulting y'all. 3.7. So the expected value, 3.7. So with this probability distribution, what's the expected value? Well, 3.7, but is 3.7 even possible? No, it's like when you see all these statistics, average couple has 2.5 children. You can't really have a 0.5 children. Okay, that's just an expected value. It's just an average. Oh, wow. And then we have a few more. Oh, I guess I'm through with all my little pretty chart here. Okay. This begins the extended conclusion for this course. We do our last homework assignment, and then we'll spend the rest of the semester reviewing for a test or taking a test, okay? Okay, a survey asked respondents how many days they had eaten food prepared at a restaurant in a previous week. Okay, so if you ask someone how many days have you eaten out this week, you couldn't get a negative answer. And also, in a 1 week's time, they couldn't give you a number bigger than 7. Okay, if they said they ate out 9 days in a week's time, then there's a serious problem here. Okay, so I'm wondering, do y'all see a negative right there? I just printed this out. Let me see. I'm going to add up all these probabilities and see, do they add together to give a 1? Did my math lab mess up? You really can't have a negative probability. Nope. In order to get all of these to add up, that number there does have to be negative. So we're still just going to go through, okay. I've never seen that happen before as many times as I've done these. I've only done this particular problem about five times. This is spring 13. Yeah, this is 5th semester I've done it. But normally you don't expect to see a negative number there. But if you're going to get the answer that they want you to get, you're just going to have to go through and do what I did. Go x times p of x, and then add them all up. And the capital letters, Greek letter sigma as a math means add them up. So I'm going to go through 0 times 0.15. Let me see. Okay, so, well, 0 times 0.15 is just 0. plus 1 times 0.25 is just 0.25, plus 2 times 0.22, plus 3 times 0.14, plus 4 times 0.12, plus 5 times 0.09. Here's the crazy thing, plus 6 times a negative 0.01, plus 7 times 0.04. Hopefully when you regenerate, or when you do your problem, there won't be a negative there. There's some sort of programming error there. But in order to get the answer they want you to get, you're just going to say, okay, pretend that it isn't negative there, and go ahead and do the little calculations. Y'all see what I did? This times this, plus this times this. Oh, it's sort of hard to see, plus this times this, and so forth. Okay? And here's a better one. Why am I saying this one's a better one? Well, do I need to draw some lines in this? A table isn't a table if there aren't any lines. Someone said that to me years ago. I'll always remember that. So here, this one's okay. There's none of those probabilities are negative. So I'm going to clear it out. And let me see. 0 times 0.01 plus 1 times 0.08 plus 2 times 0.18 plus 3 times 0.22 plus 4 times 0.31 plus 5 times 0.11 plus 6 times 0.09. Ooh. Now see what I'm doing there? Shall I write it out? 3.43. Now what was this? I never even read to see what the heck the table was. A used car dealer gets complaints about his car as shown. The number of complaints per day. So he's never had more than 6 complaints in a day. I guess if he gets 6 complaints in a day, he closes so he can't get more than that. Okay? Oh wow, the probability you get 6 complaints in a day is pretty high, isn't it? So I guess he does close at that point, because it seems like maybe he could have gotten 7 or 8 complaints. So what's his expected number of complaints? 3.43. Well, you can't get 0.43 complaints, but still, this is just an average. An average. Any questions? Moving on along. Remember teaching probability theory at Baylor University. The 1 year I taught there. And oh wow, those poor. I didn't understand why first semester there. Why was I getting math for business to teach? No one wanted to teach it. It's a Baptist university, and every parent from all over the world was calling, complaining about teaching students how to gamble. I was like, we're not gambling. This is probability theory. If seeing a deck of cards has your your child gambling, well, that's not what we're doing. We're not gambling. Okay, number 17, we are not gambling. A card is drawn from a well-shuffled deck of 52 cards. So this is my little deck of cards. Find the probability that the card is a black card or a 10. Now, first of all, with a deck of cards, notice it's aces, 2, 3, 4, 5, 6, 7, 8, 9, 10, then jack, queen, and king. Half the cards are black and half are red. There's 52 altogether. Make sure you don't count anything twice here. The reason I have this so I can sort of point. It says, okay, there are 52 cards altogether. Find the probability that a card is a black card. How many black cards are there? 26. Or a 10. How many 10s are there?
4.
There are 4. But we've already counted 2 of them, the 2 black ones, right? So that's what I'm saying, don't count anything twice. That's why Jared said 2, when I was trying to say there are 4 10s. There are only 2 10s that we hadn't already counted. So how many cards are either black or 10s? You don't count those 2 black 10s twice. There's going to be 28, and this is what, probability? So 28 over 52, which we could reduce by dividing both of these by 4. So 7 over 13. 7 over 13. Number 18. You are dealt 1 card from a standard 52 deck. Find the probability of being dealt the ace of clubs. Okay, what are these? This diamonds, hearts. I always get these other 2 names confused. Spades and clubs. Which one? Is this spade?
Yes.
And this, what did you call it?
Clover.
You see, that's what I always want to call it.
Well, my mom calls it popcorn, so I call it that too.
Oh, okay, yeah. Oh, wow, it does
Yeah,
look
the
like
same letter.
popcorn. Oh, wow. Huh. They're not twins. I thought at first they were,
No.
but they're not twins. Okay, but I forgot what I was doing. Oh, wow, I'm going to have to delete this video. No, I'm not. The probability of being dealt ace of clubs. So which one did we decide was the clubs? This one here?
Yeah.
That's the clubs, the thing that I always think looks like a clover. So there's only one of those out of what? 52. So you type the fraction 1 over 52. It's got to get harder. Okay. Oh, ready for number 19? Suppose you draw a card from a well-shuffled deck of 52 cards. Find each of the following probabilities. Oh yeah, there are 2. What's the probability of drawing a 3 or a queen? Well, there are 4 3s and 4 queens, so 8 out of 52. I could divide both of these by 4. Say it again, Jordan. 2 over 13. How are we doing on time? Ah, okay, I can go real slow. No, not really. Now, what about the probability of drawing a diamond? Well, I don't know if y'all can see that, but I can see it. Diamonds right here. There are how many diamonds? 13 out of 52, which reduces to 1/4. Aren't 1/4 of the cards diamonds? 1/4 hearts, 1/4 spades, 1/4 clubs?
Yes.
Yeah. I think there's 20 problems altogether, so I'm going to flip it over. And this one is the last. Oh, wow. It regenerated. I think we may have already done it. Is that? No, it isn't. Number 17 said the probability of, no. Where did it say about a black or a 10? Fortunately, my math lab knows how to change these up and get different problems. Okay, that same deck of cards, what's the probability of getting a black card or an 8? It's pretty much the same thing, except instead of me pointing here at the 10s, I'm going to point here at the 8s. So how many black cards are there?
Oh, sorry, 26.
26 black, plus there's, how many 8s are there that we haven't already counted? There's 2. So it's going to be the same as that one. 28 over 52, which we reduce to 7 over 13. It's the introduction to probability theory. When you leave this, after you do this, you'll know a little bit about probability, difference between odds and probability, and just basic probability. Any questions over any of this? We began with sample space. We're ending on a light note.
It's a lot easier than
I know.
Yes. If I haven't broken your spirit, if this class hasn't, it's not going to. Okay.